Hello everybody and welcome to our 5.2 concept video where we're going to continue looking at applications of integration. And this one's very closely related to the stuff we learned in chapter 3, where when we were looking at growth and decay models of exponential functions, we looked at future value and present value. And if you remember, these were really just opposite equations because the way future value worked is you took your initial amount that you invest, multiplied it by e to the kt, where k is your interest rate and t is your time, and it would give you how much it's worth after a certain number of years. Present value is the opposite. You take how much you want after a certain amount of years, or how much it's worth in a certain amount of years, multiplied by e to the negative kt in order to get how much it's worth right now, or how much you should invest right now. But with both of these situations, we're really dealing with just a single amount that we're investing. And that's kind of limiting. So what 5.2 does, what this section does, is ask the questions, how does my money grow if I'm actually adding to the account regularly? Which is more realistic, right? If I have a savings account, I'm not just adding to it one time, I'm going to keep adding to it every month or every year. We call that a continuous income stream. So once again, this section asks that question, how does my money grow if I have a continuous income stream? Well, let's think about this by using a simple example. Let's say I invest money in a bank. We'll put the interest rate at 5%, and we're going to assume that we're compounding continuously. Remember, that's important because that's what allows us to use these equations with base E, is we're assuming that we're compounding continuously. And I need a set time here, so I'm going to say for 4 years. We're going to invest money for 4 years in this bank account. But instead of me just investing a certain amount one time and then not touching it for 4 years, instead, let's say that I want to invest $50,000 each year. So I'm going to put $50,000 into my account each year, and I want to see how much I'm going to have in my account after those 4 years. Well, if I oversimplify this here, I'm going to oversimplify this. But if we just think about how this would work, let's think about my initial amount that I put in. So at the beginning of the first year, I'm going to invest $50,000. And that's going to grow over the course of these 4 years. And I can model that using my future value formula. So e to the 0.05 times those 4 years that it gets to grow. But then what happens when the next year happens? At the end of the first year and in the beginning of the second year, I'm going to invest another $50,000. But what's true about this $50,000 is it doesn't have as long to grow. It only has 3 years to grow because I'm investing this at the end of the first year. 1 year has already passed. Well, I can do this again. At the end of the second year, I'll invest another $50,000, but this $50,000 only has 2 years to grow. And then, of course, I'll do this one more time where I'm going to invest $50,000, but this last $50,000 only has 1 year to grow because this is happening at the end of the third year. To get my total amount, I'm going to add all these up. Well, what is this starting to feel like? You're calculating your values and then adding them all up. This is kind of feeling like a Riemann sum. Well, if it's a Riemann sum, that probably means it's related to area under the curve, which means I can use integration. And that's exactly what we're going to do. Once again, this is oversimplifying it. The true way we're going to do this is we're going to actually use integrals to model this. So it turns out my future value, your formula sheet actually changes the variable here. So if you see B, it's really just talking about the future value. I can calculate is using an integral from 0 to capital T. We use capital T to represent a fixed amount of time of a function r of t, which I'm going to talk about that in just a little bit, times e to the k of capital T minus t dt. And if you look closely enough at this, you can maybe start seeing connections between this and what we did in my super simple model over here. But what is that r of t? This r of t right here represents the continuous income stream. In our simple example over here, what's my continuous income stream? It's $50,000 because I'm adding $50,000 each year. But you'll notice that I wrote this as a function. meaning that this can depend on time. You might not be always adding 50,000 each year. Maybe you add 50,000 the first year, but then the next year you add 60,000. And the year after that, you add 70,000. So this could be a function. Well, turns out I also have a formula for present value. Sorry, typo from earlier. Future value actually uses the variable A, not B. Present value changes the variable to B. Well, present value formula, similar. I'm doing this integral from 0 to t times my revenue stream, my continuous income stream, times e to the negative kt dt. And that'll give me how much this continuous income stream is worth as a lump sum at the beginning. Well, like I said earlier, your continuous income stream doesn't have to be a constant amount. I can change that. If that's the case, though, then this function will depend on t, and this function depends on t, meaning, how do I integrate this? It would require integration by parts, which of course we know how to do, but it does get pretty complex. So to save us from this, what's nice, this is abbreviated calculus, or we're not going to go super deep into all of this stuff. What we're actually going to do for this section is we're going to assume that your income stream is constant, meaning you're always contributing the same amount to your account every single year. You're always adding the same amount. Well, if it's a constant, then I can just write that as capital R instead of R of t because it's staying the same. It doesn't depend on t. Well, if I do that, then my integration actually becomes much simpler. Since R is a constant, I can pull it out in front of my integral, and then I just have this integral of e to the negative kt, which we have an antiderivative formula for. So by assuming R is a constant, we can actually get a much simpler formula out of this. That doesn't actually require integration because the integration's already done for me. And the same thing is true with future value. If I assume that R is constant, I get a nice, easy formula, or I get a much simpler formula that doesn't require integration. Just to be clear, R is your continuous income stream, and K is your interest rate, and T is your fixed amount of time. But honestly, that really takes care of the concept behind this section, because with your homework, you're going to be looking at different examples of this, but in all the cases, we're going to be assuming that your income stream is constant, meaning you can just use either one of these formulas, depending on whether it's asking for present value or future value. So in that case, go ahead and get started on the homework, see how you do, and if you get stuck, you can go ahead and check out my examples video. But a little word of warning before you start the homework. There are at least 3 questions that don't actually involve a continuous income stream. And if it doesn't involve a continuous income stream, then I can just use these basic formulas that we learned in chapter 3, because it's just involving a single amount that I'm investing one time in order to get my certain future value or get my present value. So make sure you're reading the problem carefully and deciding whether the example includes an income stream, has a continuous income stream, or whether it doesn't. And it just uses these simple present value and future value formulas. But good luck, and I'll see you in the examples video.